In the previous lesson, we talked about electric charge. But did I talk about electric discharge? In this lesson, I'll talk about that. But more importantly, we'll learn about lightning and earthquakes. Air normally doesn't conduct electricity. But if the amount of electrical charge between the two bodies is extremely huge, in thousands of volts, then even air conducts electricity, which travels through it in the form of a spark. And this process is called an electric discharge. We'll now learn more about it by exploring a powerful natural phenomena called lightning. The electrical nature of lightning was first observed by a scientist called Benjamin Franklin. During the rainy season, dark and thick layer of clouds build up in the sky. These clouds are made with water droplets created by the moisture in the air, and as the clouds move with the winds, these droplets keep rubbing against each other and friction builds up a positive charge in the smaller droplets which go higher in the clouds, and a negative charge gets built up in the heavier droplets that stay lower in the cloud. This way the top of the cloud becomes positively charged and the bottom becomes negatively charged. Now if the cloud was just one solid object, nothing would happen. But since the cloud keeps changing shape and mixing with other clouds, these opposite charges can suddenly multiply, and when these huge positive and negative charges meet, there is a flash that travels along the zigzag lines of where the charges are meeting. It's something like this. This flash is caused because the air suddenly heats up and explodes as these huge charges are meeting. This flash is called lightning, and it can remain within one cloud or go across many kilometers across the sky to other clouds, or it can even go from the clouds to the earth. If it remains within the clouds, then it's called sheet lightning, and if it hits the ground, then it's called fork lightning. Now along with the lightning, there is also thunder. And that is obvious because it's the same principle of a firecracker. When a firecracker explodes, the explosion creates the light that we see, and the heat expands the air suddenly, and that expansion creates large sound waves that we hear. Same is with the lightning. The air gets heated many more times than any firecracker, and that creates the sound waves that we hear as thunder. You will notice that if you see lightning happening far away, then you can hear thunder much later. And that's because light travels much faster than sound. Light travels at 300,000 kilometers per second, while sound travels only at 330 meters per second. So it's so much slower to reach your ears. Let's look at the dangers of lightning. The electrical energy of the lightning is so huge that it can destroy anything it strikes on earth. When it hits a tree, the tree literally explodes. Humans and animals too can literally burn out if the lightning strikes them. In a building also, lightning can crack the structure of the building or even bring a small building down. And since lightning is coming from the clouds above, the taller buildings would get struck first. But then we humans have found solutions to most problems. And that's why we don't see tall buildings or even short ones being struck by lightning. Every building is fitted with a metal structure called the lightning conductor, also invented by Benjamin Franklin. This is always at the tallest part of the building. So if the lightning heads to the building, it will strike this conductor first. The conductor is connected with a thick metal strip all the way to a metal plate that is put deep into the ground. And this circuit takes all the electrical charge of the lightning from the conductor on the top of the building into the earth without affecting the building at all. So if there's a lot of lightning happening where you are, you should know how to protect yourself. Because I'm sure by now you are clear about its powers and how dangerous it can be. If you are indoors, remain indoors, because now we know that all buildings are supposed to have lightning conductors. If you're watching television, switch it off and unplug the television, because if it's connected to an antenna or a dish antenna, lightning can strike the building and burn all the electrical circuit in the building. For a similar reason, do not open an umbrella above you if you're outside when lightning is happening. Never stand under a tree, because a tree is more likely to be hit by lightning. If you are in a car, keep the doors and windows shut, and it's safer to remain inside than to stand outside the car. If you are on a large open ground, then remember that lightning will always travel through you from your highest point through the body until it reaches the ground. And while it does that, it will fry all the parts it goes through. The best thing to do is to crouch down in a ball-like position with your head tucked between your knees and your hands over your ears. If you are in a flight, then there's not much danger even if you are traveling through a storm, because planes also have lightning conductors that conduct any electrical charge from the tip to the tail without affecting the plane or its electrical components. Now that we are safe from lightning, let's understand things about earthquakes so that we can deal with them as well. Interestingly, storms and therefore lightning can somewhat be predicted because weather forecasters can see a storm building up. But an earthquake mostly comes with none or very little warning. An earthquake is a sudden shaking or trembling of the earth, and it generally happens for a very short time, but it can also happen multiple times. It is generally caused by violent movement within the earth's crust. The earth's crust is always moving around and causes mild earthquakes, which are also called tremors. And it happens all over the world, but most of them go unnoticed because they are not very strong. Earthquakes cause huge damage to property and life, like the one that struck Bhuj in Gujarat in 2001. When earthquakes happen underwater, they can cause giant waves hitting the land, and these are called tsunamis. And now we know about them because on 26th of December 2004, a huge tsunami hit the entire east coast of India because of an earthquake that happened in the Indian Ocean. Let's take a look at the structure of the earth to understand earthquakes better. If you cut the earth into half, this is the basic structure you'll see. First, we need to zoom out and see what are the different layers of the earth's section, from top where we stand to the center of the earth. The earth's crust is the top layer that is made of comparatively lighter rocks. This section of the earth varies in thickness because it is thicker where there are mountains rising high, and it's thinner where there are deep oceans. And this layer is not one single layer, but it's broken or fractured into what are called plates. The plates with the continents are called continental plates, and the ones with the ocean are called oceanic plates. Now, because of the movements in the mantle of the earth below, these plates also keep shifting. Now imagine this. It all looks so big, but all this is happening only in this little thickness of the earth on the top. The mantle is made of dense solid rocks, but the upper mantle has more areas of liquid rocks or molten rocks similar to the lava that comes out of a volcano. Because of the molten iron in the outer core below it, there is a lot of convection currents in this section, and it keeps the mantle moving really slowly, and that causes shifting of the plates in the crust, which is the topmost layer of the earth. The outer core is made of molten iron and nickel, and the temperature is said to range around 4000 to 5000 degrees Celsius. This section creates the magnetic field of the earth. The inner core is made mostly of solid iron and nickel. The temperature at the center is about 7200 degrees Celsius, and that's hotter than the sun, but it is still solid because of the extreme pressure around it. Now that we know about the layers within the earth, let's go again to the point where I said that shifting of plates in the earth's crust can create mountains and valleys and create the earthquakes and tsunamis. There are two ways how these shifting plates can cause earthquakes. One is by sliding past each other, and the other way is by colliding against each other. Let me first show you some clips of a landscape that will go through these two types of plates interacting with each other. Here are some aerial videos. It all looks so nice and peaceful. But when earthquakes strike, the ground trembles, and large rocks that are balanced on the edges of cliffs can roll down and cause a lot of damage if there are people living down there. But luckily no one is under this. Let us see the action from a few more angles. Now let us see what is actually happening. In this first type of earthquake, the plates are sliding and rubbing against each other. Actually, this would be happening on a much bigger scale, in the size of continents, and it takes thousands of years to move very small distances. But as they rub against each other, the surfaces are not smooth, and sometimes they lock into each other and suddenly break free, releasing a huge amount of energy. This energy can produce shock waves or seismic waves that travel through the ground, and we feel them as earth moving, and we call them earthquakes. The other way earthquakes happen is when two plates collide with each other. And when this happens, they don't just bounce away, but they keep going into each other very slowly for centuries. They keep moving into each other, and the effect is either a fold at the line of contact, as you can see happening here, or it causes a fault or a fracture at the line of contact, and that's happening here. Once again, let's see how the fold mountains would be created as the land masses on the plates keep rising, as the plates keep going into each other. A good example of mountains being created by folds is the entire Himalayan range of mountains. And since it's still happening, this kind of area is also called a seismic zone, where seismic activity keeps happening, causing regular earthquakes and tremors. A good example of the plates colliding and mountains rising through faults in India are the Satpura and Vindhya ranges and parts of the Western Ghats. Even though the height of these mountains is not too much as compared to the Himalayas, these mountains are made of steep cliffs that look like they've come straight out of the ground, which they have. Here you can see how the fault mountain is just beginning to be created. So these plates keep moving. In fact, it is said that all the continents were one mass of land at one point millions of years ago and have moved away from each other, and they're still moving. When the earthquake is triggered, the trigger point is called focus, and that would mostly be way underground. From the focus, there are shock waves or seismic waves that travel in all directions, and they are felt on Earth as well, and these are the tremors. The point of ground right above the focus is called the epicenter of the earthquake. Tremors would also be felt if a meteor hits the Earth or an underground nuclear explosion is carried out. A seismograph is an instrument that is used to measure and record the magnitude of an earthquake and its shock waves. We'll cover this later because I'll show you how to make a basic one in the TIY. In sound, you have learned that there is a decibel scale that shows you how loud something can be. Similarly, the magnitude of an earthquake is measured on a Richter scale. Charles Richter developed the Richter scale in 1935, and it measures the magnitude of earthquakes at a distance of 100 kilometers. Each increase of 1 unit on the scale represents a 10-fold increase in the magnitude of an earthquake. This means an earthquake of 5 on the Richter scale is 10 times more than an earthquake that is 4 on the Richter scale. We can't even feel earthquakes below 3 on the Richter scale. The Gujarat earthquake in 2001 was 8 on the Richter scale, and that's why it was so huge and caused so much destruction. The tsunami in 2004 was caused by an earthquake in the Indian Ocean that is said to be 9.1 on the Richter scale. So how do we protect ourselves against earthquakes in a known seismic zone? Buildings and houses can be designed for earthquake resistance. There are many technologies, construction methods and materials that can allow buildings to shake but not fall. Can you believe that skyscrapers can actually sway around a meter or two at the top without breaking apart? The small houses in seismic zones could be built with lightweight construction like wood and light roofing materials so that they pose less danger when they fall. Cupboards and large furniture items should be securely fastened to the walls. If you are at home when the earthquake happens and you can't run outdoors, here's an infographic poster of which you can take a screen grab and print out if you want. First thing about any emergency, don't panic. Run out if within a couple of seconds you would be outdoors. Otherwise, if you're in a building, don't try to run out. The earthquake lasts a very little time, so it is best to take precautions wherever you are instead of getting caught by something falling on your head while you're trying to run out. Inside the house, crouch under a strong table or bed and hold its legs so it doesn't move away while the earth is shaking. Standing at the corner of an empty room is safer than standing along a big wall or in the middle of the room. In a tall building, if there is a lift, don't get into it, but stand close to the outer wall of the lift. The reinforced concrete structure around a lift is generally the strongest vertical structure in any tall building. Stay away from stairs. After the earthquake is over, keep your head protected and find your way out. Turn off gas and mains for the electricity. Extinguish any fire that you might see. If you're outdoors, when an earthquake happens, stay away from tall buildings or any structure that might fall. Run to higher grounds and stay aware of rolling objects. If you're in a car, stay in it with the doors and windows closed, and it's best to be on clear open ground. Stay away from electrical wiring. After the earthquake is over, get to an assembly point if there is. Help your neighbors, help with first aid, and stay aware of what all is happening in your neighborhood. Let's do a recap and dive into the TIY of this lesson. What is lightning? If the electrical charge between two bodies is extremely huge, then even air conducts electricity in the form of a spark, and it's called an electric discharge. Friction in water molecules in a rain cloud builds up electric charges. Large charges meet with a huge electric discharge through the air. These are called lightning. If lightning remains in the clouds or goes across the sky, then it is called sheet lightning. If it leaves the clouds and hits the ground, it's called forked lightning. The lightning causes air to expand rapidly, creating thunder. Light travels much faster than sound, therefore we hear thunder much after the lightning. Dangers of lightning. Trees or parts of trees can literally explode if lightning hits them. Humans and animal cells can burn out with a lightning strike. Lightning can crack the structure of a building or even bring a small building down. Lightning can destroy electrical devices if it hits electrical wiring connected to it. Lightning will hit the taller structure if two similar structures are side by side. Safeguards and protection from lightning. The buildings have a lightning conductor that takes all the electrical charge of the lightning from the top into the earth without affecting the building. There are do's and don'ts to protect ourselves when we are indoors or outdoors during heavy lightning. Planes have lightning conductors and therefore it's safe even if they go through thunder clouds. Earthquakes. Earthquake is a sudden shaking or trembling of the earth caused by violent movement within the earth's crust. Earthquakes can cause a lot of damage to property and life. If they happen in water, then they can cause tsunamis, and these are equally destructive. The different layers of the earth from top to center are crust, mantle, outer core, and inner core. What causes earthquakes? Crust is fractured into many pieces called plates. The plates with the continents are called continental plates, and the ones with oceans are called oceanic plates. They can cause earthquakes by sliding past each other. They can cause earthquakes by colliding against each other. About the earthquake, the point of origin is called focus. The point on the ground right above the focus is called the epicenter. From the focus, there are shock waves or seismic waves that travel in all directions. These shock waves are also called tremors. A seismograph is the instrument that is used to measure and record the magnitude of an earthquake. The magnitude of an earthquake is measured on a Richter scale developed by Charles Richter in 1935. Safeguards and protection from earthquakes. There are methods of constructions and techniques to safeguard from earthquakes. There are do's and don'ts to protect ourselves when we are indoors or outdoors during or after the earthquake. There's always a standard seismograph that is shown in most of the textbooks, and we'll first make that to understand how it works, and then I will also show you a problem that needs to be solved to make it work well. And that's the big difference in a DIY project, where I'll discuss what works and what doesn't work so that you can choose how you want to do it. This is the basic structure from one of the earlier lessons, so I won't repeat the dimensions of this part, but we'll use most of it and add more parts to make this DIY project. Add the corner joints as shown, then add the 17 cm pipe, then another corner joint, and then the angled or cut pipe, which is 14 cm. Put them together as shown. Same on the other side. Tighten the joints by hitting with a mallet or a wood piece. We avoid metal hammer so that the pipes don't get damaged. Add the 21 cm piece for the vertical stand and then the T-joint with the hole facing forward. Now put the earlier vertical and the top part back on the T-joint. Tighten all these parts. Use glue if the parts keep moving. Now take the big pipe. You need to cut some strong cardboard to make two circles that fit inside the pipe. I'm using an old box file that we keep using when we need strong cardboard. Use a compass to draw the circles. We need the circles to be 15.5 centimeters, which is equal to the inside diameter of the big pipe. After marking the circles, cut it. I'm using a hacksaw blade. You can tape up one side of the blade so that it doesn't hurt your hand. Here's a tip. Rub the blade on any object. It should cut when you push and not when you pull. Once the circles are ready, make holes in the center of both the circles with a compass. This is for putting the bicycle spoke inside it. Be careful that you don't poke the other hand while making the hole. Put the first circle into the pipe. Keep it about 1 centimeter inside the end of the pipe and then glue it. This way the glue should remain inside the pipe. Now you need to put the spoke through the first angled pipe and through this cardboard that's fixed to the big pipe. On the other side, put the spoke through the second cardboard and then put the cardboard inside the pipe and push it 1 centimeter inside. Don't worry about exact measurements here. Put the spoke through the other angled cut pipe and screw on the spoke head. Check if this drum rotates freely, and then glue the other cardboard as well. Remove any glue that comes out of the pipe edge. Let's prepare the weights now. Take the 1 kg weight and glue the small PVC pipe on it as shown. Put the other weight on top and then first tape it to hold it in place while the glue sets, and once it has set, tape it up properly as shown. Now we need to make a small hole through one end of the pipe. With PVC, if you don't have a drill, then heating a spoke or a metal rod to make a hole is good enough, but make sure you do it in a ventilated room because the fumes are toxic. We need a strong nylon thread of about 2 meters, and again at the halfway point, double it and put it through this hole. But it's not that easy, as you can see. But then there's a trick you could use using a thin wire. Loop the thread as shown, and it will hold the pipe straight when it hangs. This pipe was chosen because it is slightly fatter than the pen so that the pen moves smoothly in it. Now measure the length of the thread such that the pipe hangs close to the drum without touching it. Tie a knot and then hang the weights as shown. Cut out the extra thread. Put the pen in place. Now you can see it right when the drum is rotated. Now see this problem that one doesn't realize until you make it. When the earth shakes, it could move the drum in any direction, and therefore the weight would start swinging in any direction. But we need it to swing only along one axis, and that is along the top line of the drum. So for that we'll go to part 2 of our build and get to a new improved version. Now cut a 5 cm wide strip of plastic sheet, or flex as it's called. Let it be about 2 meters long, even though we need less. At the halfway point, fold it and cut out a hole of any shape. A round is good, but the diamond shape is easy. Put the pipe through this hole and hold the weights as shown. You can tape it in place if you want. Put this belt over the top pipe once again such that the pipe with the weights is close to the drum below. And then you can even simply clip it in place. Now you can see that the weight will swing in one direction. It will be best to align the drum perfectly along the swing by twisting the supports as required. Now when the earth shakes, and if the drum is rotating, you will get a better indication of the magnitude of the shake. But we need to move the drum really slowly, so I am using a geared motor that is available on the net for very little cost. Find a plastic cap of a pen that will fit on the shaft of the motor and cut a small piece and glue it and hammer it in place. Put a double-sided foam tape around the drum along one side. I am using the finger here to remove some of the stickiness from this side of the tape. We needed to grip the motor but not stick to it. You can also use powder. Now glue the motor such that the new shaft is gently pressing against the foam tape. Secure the motor with more tape. Connect the motor to 3 to 6 volt batteries or a battery eliminator. Make sure that the drum rotates in the forward direction as shown. You can see when the earth shakes, this is now behaving much better. Once again, another problem that I noticed is that the weight keeps swinging, but we need to reduce the natural swing. For that, we'll go to part 3 of our build. Fix the other set of PVC pipes and fittings in the T-joint of the vertical structure as shown. Make sure that these arms are close to the drum but not touching the drum. Tie 2 rubber bands to each other and place them like this. Tie 2 more for the other side. Put the free ends of the rubber bands around the bottom of the pipe as shown. This will help us restrict the swing. Let's see if it works. it works well enough to bring the swing down much faster. You could also attach a roll of paper by sticking the front part on the drum as shown. So we have a seismograph that works. It's not perfect, but it will still give you a good idea of how the actual seismograph works. Things required for the DIY project. PVC structure from one of the previous lessons. New PVC items, the dimensions are listed earlier. Mallet, or you can use something else. Big pipe, 25 centimeters long and 15.5 centimeters diameter. Scale, box file or strong cardboard. Pencil and compass. Hacksaw blade. Insulation tape. Bicycle spoke with spoke head. Glue gun, 1 kg weight, 2 pieces. Small pipe, 10 centimeters long, 1 centimeters dia. Candle, nylon thread, 2 meters long. Thin strand of wire. Sketch pen, flex or plastic sheet. Scissors, butterfly clip or any strong clip. Geared motor. A sketch pen cap. Double-sided foam tape, rubber band 4 pieces, A4 size sheet 3 to 5 sheets. Did you learn anything earth-shattering in this lesson? I think you did. There's so much more to learn. In the next lesson, let's have some light fun, especially because it's on the topic of light.